Hi, and welcome to the first academic video of this channel. Today we're going to be talking about Chapter 19 in the Year 2 Chemistry textbook. This is all about equilibria. Our first lesson is going to be on Kc. Kc, as you remember from Year 12, is the equilibrium constant, and it gives us a numerical measure of the position of equilibrium when it is at dynamic equilibrium point. Kc is represented as the concentration of products over the concentration of reactants, each to their order of magnitude that you can get from the stoichiometric ratio of a balanced symbol equation. For example, if we were to do NH3 goes to nitrogen and hydrogen, this is the reverse equation of the Haber process. That gives you 3 hydrogens. The Kc could be represented as, for the reverse reaction, so not for the forward reaction, Kc could be represented as N2H2 cubed NH3 squared. So, as you can see, the cubed bit for the hydrogen comes from the fact that we have 3 hydrogens in the balanced symbol equation. Again, that's for the 2. And that we have our reactants, which here would be NH3, on the bottom, and our products, which is nitrogen and hydrogen, on the reactants, on the top, sorry. This is uncommon for seeing this one, because normally you'll see it the other way around, because the Haber process is normally defined as the reaction of nitrogen and hydrogen to form ammonia. But that, I think, is a good example of showing how Kc is written. You'll also be expected to calculate the units of Kc in any particular reaction. And the way you would do that is, say again, for this reaction of 2NH3 goes to N2 plus 3 hydrogen. Let's say you represent the equilibrium again as we did before, and we did the Kc as before. What you can do is you can put the units on the top. So you can put all the units in there. So as you know, all the all the concentrations are moles per decimeter cubed. So you'll have, again, don't forget the stoichiometric ratios on each of the as the order of magnitude. So as you can see from this, you have 2 moles per decimeter cubed on the bottom, because you have 1, and then you have that squared, so there'll be another 1. And on the top you have 4, because you have 1 here, and you have 3 in this, because that's that to the power 3. So what you can do is you can just cancel the powers, and you can cancel it, 1, and you can get rid of that. So you've got rid of the 2 from the bottom, and what you've done is then you've got rid of 2 out of the 4 that were on the top. Now, what that leaves you with is Kc equals mole dm minus 3 squared, which is mole 2 dm minus 6. Because you remember from GCSE maths, from your index laws, when you have a bracket with indices to the power of anything, you then just multiply the indices to get what the new is, to expand that. And here you technically have mole 1 dm minus 3. So you can times 1 by 2 to get 2, and you can times minus 3 by 2 to get minus 6. So overall, to work out the units for Kc, what you do, 2 steps. You substitute units into Kc expression, and then you cancel and simplify the units. Units. I'll just give you a couple of seconds to take that down. Then we're now going to talk about homogeneous and heterogeneous equilibria and calculating Kc when you're given equilibrium moles. So x and y here are the stoichiometric ratios from the symbol equation. Sorry. Cool. We can now move on. So homogeneous equilibria are, homo comes from Latin meaning same, and genus in chemistry usually means phase or state. So you may have heard the phrase homogeneous when you're talking about catalyst, and a homogeneous catalyst is one where the catalyst is in the same phase as the reactant. Phase is often used interchangeably with state at A level, and so what that means is, say you have a reaction using solids, if your catalyst is also a solid, it is a homogeneous catalyst. And here, your homogeneous equilibria is one where all the species of the equilibrium are in the same state. I.e., again, we can talk about the Haber process again. We can say N2, which is a gas, plus 3H2, which is a gas, gives you 2NH3, which is also a gas. And since they're all gases, so in same phase, so homogeneous. A heterogeneous catalyst, or a heterogeneous catalyst, is one where the catalyst is in a different phase to the reactant. So a heterogeneous equilibria hetero is different, genus is phase, so it's one where the species aren't all in the same state. In a homogeneous equilibria, when you're doing a Kc expression for it, if they're all in different states, then not all the species are involved in the Kc. So in a homogeneous equilibria, the Kc contains all the species because they're all in the same phase. Whereas in heterogeneous equilibria, the concentrations of solids and liquids are constant, so anything that's a solid or a liquid is omitted. So we only use, for heterogeneous equilibria, aqueous plus gases. So for example, if we had the equation of carbon, which is a solid, plus 3 hydrogens, which are all gases, to form carbon monoxide, and 2 hydrogens, which is a gas and a gas. You can omit the one that's a solid, because a solid, you can't really measure the concentration of a solid because that's a constant. So we'll only use the phases, only use aqueous or gases in our equilibrium expression. So for this one, the Kc expression would be H2 squared CO over H2 cubed. And if you can guess what the units are, pause and try and work out what the units would be. Give you a second. Yeah, so for this one, there's no units because you have 3 on the top, 3 on the bottom, they all cancel out, so you'll have no units overall. We're now going to talk about something called ICE equations or Rice equations. / calculations. And this is the way to calculate, sorry about that. Calculate Kc when given moles initially in mixture. So this is not when you're given concentrations that you just plug into the expression. This is more of a calculation that you work through when you're calculating the number of moles if you're given them initially. If you're given number of moles initially. So let's talk about the Haber process. So quickly write it out again. Gives you N3 times 2. So a scientist, let's say he puts in 1 mole of nitrogen, 3 mole of H2, and he wants to calculate Kc. He wants to calculate the equilibrium constant. So how would you go about doing this? So what I would do is I would write ICE down the side of your page if you're given this in an exam, and at the top, like you would for a just write your species. ICE means I means initial, C means change, and this is equal, and this is a ratio. So the ratio you can get from your stoichiometric ratio. So here's 1 to 3 to 2. Your initial you know from your question, and you know that initially you'll have none of your product because again nothing has reacted yet. You're also in the question you'll also be told something, so you'll say at equilibrium uh, 1 mole of hydrogen remains. So then you know at equilibrium you've got 1 mole, so you know the change there is -2. Alright, so what you can then do is you can then work out the change in this. So if 2 moles are taken from the 3 here, how many moles will be taken from here, from the nitrogen? Remember to take into account your ratio. So here is a 3:1 ratio, so it's -2/3 moles because you've divided the change by the basically the ratio, and that gives you 1/3 equilibrium. And for the NH3, So let's try this again. Remember, product you're adding, it's not being reacted, so it's not being taken away. So you're creating more product, and you're creating, how much are you creating? So you've got minus 2/3 here. It's a 1 to 2 ratio. So you multiply this minus 2/3 by 2, so it's 4/3. And remember you're adding, so it's plus 4/3. So at equilibrium you have 4/3. Now this gives you the number of moles. That gives you the number of moles. In a question, you'll have to convert to a concentration, because Kc uses concentrations. So what you then do is you use your equation that you remember from GCSE or Year 12, N equals CV. To work out concentration, you're using N, which is the number of moles, and the volume. So you're doing the number of moles divided by the total volume. So the question will then give you a total volume, and the total volume of a container might be 1, maybe 2 decimeters. Usually in the exam they won't give you sort of odd numbers or weird things to calculate. And then you divide so to work out the concentration of each species, you divide the equilibrium moles by total volume, and then you place the entire thing into your Kc expression. This might seem a little bit overwhelming, so let's do a worked example together, and I'll kind of explain how each step goes. Then we can talk about, that's pretty much it for Kc. So we'll do a work example, and then I'll give you a few to sort of try on your own. We're going to talk about the contact process here, which is so that's the contact process. Sulfur dioxide is converted into sulfur trioxide. So first I would write an expression for Kc, which is, remember they're all going to be in gaseous state. So it's SO3 squared over O2 times SO2 squared. That's your expression for Kc. Remember, again, another sort of pointer for exam technique, always remember the square brackets. Square brackets mean concentration, and when we talk about Kp next week, we'll talk about partial pressure, and that will be round brackets. So, yeah, remember to use square brackets. The question will say 1 mole of O2 added 2 mole of SO2, right? 0.25 mole of O2 remain at the equilibrium point. Container of 1 dm cubed. So let's do the ice. So we're doing 2 to 1 to 2 ratio, SO2, O2, SO3. Initially you have 1 mole of that and 2 moles of that. You minus 0.75 because you're having 0.25 moles at equilibrium. Now, for this, you times that by 2. Times that by 2, you get 1.5. You're taking 1.5 moles away because it's a 1 to 2 ratio. So as you can see, we're timesing that by 2, so you're going to times that by 2. So you're going to take away 1.5 moles, which gives you 0.5 remaining. Here again, you'll add, there's 0 at the beginning, you're now adding because it's the reactant. So you're adding 1.5 moles. So you then get 0.5 again. Oh, sorry, you get 1.5, not 0.5, because 0 plus 1.5 is 1.5. Now you've got the number of moles. What you then do, so this one we're quite fortunate, it's a 1 mole per decimeter cube container. You'll do concentration of SO2 equals 0.5 over 1, which equals 0.5. Concentration of O2 equals 0.25 over 1, which equals 0.25. And the concentration of SO3 equals 1.5 over 1, which is 1.5. To finish, what you got to do is now plug those values into the case C equation. 1.5 squared over 0.25 over 0.5 squared, which equals, let me get my calculator for a second. You can just plug this into your calculator now. Give you a second to work it out. Which is 36. And just as a final flurry, let's calculate the units. You've got 2 on the top, 3 on the bottom, which means that it's 1 over mole per dm minus 3, which is mole to the minus 1 dm to the 3. Because again, you just, as you remember from your GCSE inverse index laws, you flip the sign when you're going from the top to the bottom. So, for example, 1 over 2 is equal to 2 to the minus 1, if that makes sense, because 1 over 2 to the 1. So just remember that when you're flipping it, it should give you the opposite sign, the same number, opposite sign. That will make sense. Cool. A few exemplar problems. One exemplar problem for you guys, and then we'll see if you can. Then I'll let you get on with some practice problems. NO2 gas. You have 2 mole of that, 1 mole of that. At equilibrium, you form 1.2 mole of that. So that's how much is left. That's how much formed. Oh, sorry. Apologies again about that. Start. Sorry, it's 1.6 moles of that and 1.4 moles of that. Container has a volume of 4. And that's how much formed at equilibrium. Calculate Kc. So that's the experiment. Do you want to have a go? I'll give you a minute to work it out. Just pause the video and give it a go, and then we will carry on. Cool. I will try work through this for you. So, NO plus O2 gives you NO2 iser. So you've got a 2 to 1 to 2 ratio. Initially, you've got 1.6 of that, 1.4 of that, 0 of that. You form 1.2, so you've got plus 1.2 of that. That means that you've got minus 1.2 of that because they're the same ratio. So that's 0.4 of that. You're minusing 0.6 of this one because, again, divide by 2. So you divide by 2. 1.4 minus 0.6 is 0.8. Put that in, substitute that into your Kc equation. However, that's the number of moles. So the concentration of NO is 0.4 over 4, which is 0.1. Concentration of O2, 0.8 over 4, 0.2. And the concentration of NO2 is 1.2 over 4, which is 0.3. Substitute that into your Kc expression. So 0.3 squared over 0.2, 0.1 squared should give you a final answer of 45. Just make sure you've got your units. You've got 1 over mole dm minus 3, which is mole minus 1 dm cubed. Final point on Kc, just as a last thing to talk about. Kc is only affected by temperature. Kc is not affected by any other factor. So constant, even if pressure changes. A catalyst will speed up the rate of reaction of both the forward and reverse reactions equally. Oops, sorry. Hope you enjoyed that video. So the Kc remains constant. Finally, to conclude, hope you guys enjoyed that video, and if you have any issues with this topic, if you have any issues with this topic, put it in the comment section, and make sure you subscribe for more of these types of videos. In the description, I've put a link to Physics and Maths Tutor and a few other places where you can go to find practice questions, because they're the best way to practice these types of things. There's a textbook page reference for the Oxford textbook. In there you'll find some summary questions for this stuff, and it will just talk about all of that stuff. And next time I'll talk about Kp and the position of equilibrium, which is all about Le Chatelier's principle and stuff. So yeah, that's it. Thank you guys. Bye.